Are atoms real?
Nobody has ever seen an atom. Yet scientists count them. They even build wire models which show how atoms are arranged in space. But if atoms can be counted and located and weighed, then surely atoms are real.
Atoms real? But of course. If the chap who asked the question had only said, "Are flying saucers real?" we might have had something to argue about. But atoms, after all, this isn't 1810 or 1910, this is today.
But you can't see them.
What of it? You can't see air, but you can breathe it and feel it pushing against you on any windy corner. Things can be real without being visible. But come to think of it, we're being a bit superficial. Our question, are atoms real, invites us to do some hard thinking about the word real and about what the scientist knows about atoms. After all, the word real is one of the most important in the language and more than a little tricky. We all use it and have a feeling for its meaning, but there isn't any clear and generally accepted definition. All of us will agree, I suppose, to the importance of a proper sense of reality. The feeling for the distinction between reality and illusion, reality and fiction, reality and myth. This is the mark of sanity, maturity, and education. An insane person is one who lives in a world of delusion, out of touch with reality, because he cannot face it. A child who daydreams over much and spins fantastic stories has a child's imperfect feeling for reality. The ignorant, superstitious, and credulous are like the child in their imperfect sense of reality. Among primitive men, fact and fancy have always been fantastically intertwined. The archaeologists tell us that in the ancient civilizations of Egypt and Babylon, the sharp distinction we draw today between dreams, hallucinations, and normal sight was not generally drawn, nor was there a clean separation in thought between appearance and reality. It was the Greeks who first interpreted the world directly revealed by our senses, the world of light and color, sound, taste, smell, and touch, as a world of appearance behind which there must be a world of reality. From this point of view, we can regard science, which began with the Greeks, as an attempt to lay bare the real world behind the camouflage of appearance. You see, a rod thrust obliquely into the water appears to be broken at the water surface, but in reality it is as straight as ever. The sun appears to rise in the east and sink in the west. In reality, according to Copernicus and Galileo, the sun stands still. It appears to move only because we see it from a moving earth, which spins on its axis as it slowly swings around its sun-centered orbit. Reality suggests truth. In fact, truth is sometimes defined as agreement with reality. Thus, the scientific exploration of reality is a part of man's great quest for truth. And the scientific way of getting at reality is his most powerful aid in the search for truth. From this point of view, the deeper the scientist goes in his exploration of the physical universe, the more he understands, the closer he is to reality. If the real world is what lies behind the world of appearances, then the world of atoms, electrons, photons, and electric waves disclosed by modern science can well be regarded as the real physical world. So let's look at this world of atoms. Physicists and chemists believe that matter is granular, that it is composed of particles. We call them atoms, too small to see individually even in a high-powered microscope. They tend to unite in small, tightly knit groups called molecules. Sometimes the atoms remain single. In this case, we call them single atom molecules. Please note, the distinction between atoms and molecules is, for many purposes, unimportant. Do not worry if I sometimes seem to use the words interchangeably. A sample of any pure substance consists of an enormous number of molecules or atoms of the same species. They are conceived to be in perpetual, chaotic, haphazard motion. We call this invisible motion of invisible particles thermal agitation. The energy of this motion is heat. The intensity of the motion is measured by temperature. As the temperature rises, the pace of the motion is increased. As the temperature falls, the motion slows down until, at the absolute zero, 460 degrees below the ordinary Fahrenheit zero, to all intents and purposes, it ceases. This conception of matter and heat helps us to understand the three fundamental states of matter: solid, liquid, vapor. In solids and liquids, the molecules are huddled together, whereas in a vapor or gas, they are relatively far apart on the average. Solids and liquids are held together by strong forces of attraction which atoms and molecules exert on each other when in contact. In a vapor, on the other hand, the attractive forces are unimportant. Most solids are crystalline. Whether the crystals are small and mashed together, as in this piece of granite, or whether they are separate, as in these other cases, this is quartz and rock salt. In a crystal such as rock salt, the molecules form a regular pattern, like the cells of a honeycomb. Each atom and molecule is bound to a fixed position by the attractions of its neighbors. The pattern of this structure determines the natural external shape of the crystal and the shapes of the pieces formed when it is broken. Let us now try to imagine what goes on inside a solid as it is heated up. Let me show you a crude model of a few atoms or molecules in the interior of a solid at the absolute zero. Each rests at its fixed equilibrium position. As heat is added, the molecules are set into vibration. At higher temperatures, the pace of the motion increases until finally it disorganizes the whole structure. The attractive forces are no longer able to hold the molecules near their home bases. The material loses its definite form and melts. It now forms a liquid that accommodates its shape to that of any containing vessel. This is what happens when we melt a candle. In the case of a liquid, the binding forces, though insufficient to maintain a solid structure, are still able to keep the molecules huddled together in a compact mass. If a molecule on the outside of a drop of water is given an accidental shove toward the surface, the combined attractions of its neighbors are usually able to prevent its escape. Occasionally, however, the accidents of the thermal dance will give a surface molecule a much larger push than usual, with the result that it does escape from the drop into the surrounding air. The molecule evaporates. It enters the vapor state or gaseous state. In ordinary air or steam or any gas, the molecules are far apart on the average. They collide with one another, but most of the life of any molecule is spent so far from its neighbors that it lies beyond the range of their attractive forces. The molecules are free, aside from occasional collisions. This is only a suggestion of the way in which the molecules move. Actually, the molecules in a gas move at high speeds, in straight lines, interrupted occasionally by a collision. Because a gas, in comparison with a liquid or solid, is a thin population of molecules, the gas has no cohesion, and it expands to fill any container in which you put it, like this. I've been describing very briefly the three states of matter: solid, liquid, and gaseous, in terms of the atomic molecular theory. In other words, I've been giving you glimpses of the world of atoms. Let me assure you that such pictures shed a flood of light on the behavior of matter when it is heated or cooled, compressed or expanded. The atomic picture is equally useful in the interpretation of chemical reactions. Each element is conceived of as composed of a corresponding species of atoms. When two elements unite to form a compound, the atoms of the elements are combined to form molecules of the compound. Water, for example, is a compound composed of molecules, each of which contains two atoms of hydrogen and one of the element oxygen. This conception finds thousands of confirmations in the detailed study of chemistry. There are no chemical or physical facts with which it does not harmonize. Moreover, the atomic theory has served not only to explain the already known facts about the physical and chemical transformations of matter, it has suggested an enormous variety of experiments that in turn suggest new facts about atoms, their structure and properties. In the light of our constantly growing knowledge of the details of the world of atoms, we are able to understand such things as why glass and alcohol are transparent, while iron and copper are not, why a clean surface of silver gleams, why a mixture of gasoline and air explodes violently when lit by a match. We understand, too, why there are 91 elements found in nature that have atoms lighter than uranium, and no more. Why radium, thorium, and uranium are radioactive, while oxygen, nitrogen, and iron are not. How it is that the sun has been able to pour out vast quantities of heat for billions of years and does so still. These are deep questions. 50 years ago, one would hardly have dared ask most of them. Today, we ask them and we know the answers. And knowledge of the world of atoms brings power as well as understanding. Power to control chemical processes, to create a vast variety of new and useful materials, such as nylon. The technological achievements of modern America rest firmly on our understanding of the world of atoms. In fact,